we present reference-guided controllable inpainting of neural radiance fields. To inpaint a nerve scene, in addition to the conventional nerve inputs and the mask of the unwanted object, we ask the user to provide a single inpainted view of the scene, which we call the reference view. The reference view provides guidance for the generation of the inpainted scene. Users have control over the generated scene by changing the single reference view. The reference view can even contain novel objects like the duck in this example. Consider this piano scene full of reflective surfaces. The goal here is to remove the music sheet. For a single reference view, the user first uses an image inpainter to generate the inpainted reference view. The inpainted reference view is then fed into a monocular depth estimator to get the predicted disparities, which are then aligned to the coordinate system of our nerve model using our weighted alignment and disparity smoothing components. So far, to supervise the inpainted nerve, we use the ground truth colors of the unmasked pixels to supervise the unmasked regions of the nerve. We supervise the geometry of the masked region by the aligned disparity of the reference view. Up to this stage, the appearance of the masked region has remained under fit. Although the inpainted reference view provides some supervision for the masked region's appearance, it lacks the information about potential view-dependent effects from other views. To address this issue, we propose our view substitution method. Our view substitution component enables us to look at the scene from the reference view while substituting the colors with the colors of any target view. This enables propagating view-dependent effects to the masked region. On screen, we are showing different view-substituted nerve renders. Notice how the view-dependent effects are changing, such as lighting specularities in the masked area, but the camera position and image structure is not changing. Also note that as a result of our view-dependent handling component, the view-dependent effects inside the masked region are consistent with its surrounding. Let's see how this works in practice. In typical volumetric rendering of nerves, for a pixel P in the reference view, we first cast the ray through the scene. We then sample endpoints x1 to xn on the ray. For each point, we feed its coordinates along with the ray direction to the nerve model to get the colors and densities. These point colors are then integrated along the ray with respect to their densities according to the volumetric rendering equation. However, we are interested in the colors of the scene from a target camera. While rendering the color of pixel P, for each shading point xi, we use the direction of the ray connecting the origin of the target camera and xi and feed that to the nerve model. This way, we are looking at the scene from the reference camera, but rotating the view directions towards the target camera to get the colors from the target. For each target, using the reference view and the current stage of the inpainted nerve, we use our view substitution method to get the view substituted image. We then calculate the difference between the reference view and the view substituted image to get the residual. The residual is then inpainted using a fast bilateral solver to get the inpainted residual. In this stage, we are in general propagating the information about the view-dependent effects from outside of the mask to the inside. The inpainted residual is then subtracted from the reference view to get the target colors. The discrepancy between the view-substituted images and the target colors are used to supervise the masked region's appearance. We now see the utility of having the view-substituted images. Since we have the target image colors but in the reference view camera frame, we are able to combine those target colors with the reference edge structure for bilateral guidance. Briefly, recall that the bilateral solver propagates an image signal guided by the image structure of a separate reference image, effectively providing a form of guided inpainting. We have previously described our approaches to geometric supervision and propagating view-dependent effects to non-reference views. However, this doesn't cover all missing information caused by using only a single reference image. Notice that for a target view, parts of the scene might still be invisible from the reference view. We call these parts the disoccluded regions. We select the rightmost view, the leftmost view, and the topmost view, and propose an approach to provide supervision for the disoccluded regions. For each of these target views, we first detect the mask of the disoccluded region. We use the geometry of the scene learned by the inpainted nerve and back project the inpainted reference view to the 3D scene. It is then reprojected to the target view. However, some pixels of the target view remain unmatched. This gives us the mask of the disoccluded region. This mask is used to inpaint both the appearance and the disparity of the target view, which are then used to supervise the disoccluded region of the inpainted scene. Please see our paper for details and visit our website for visualizations.